In this video, let us see performance characteristics of alternator. Okay, we are not going to discuss complete performance characteristics. Let us have a split. Okay, some characteristics we cannot derive without phasor diagram, and some characteristics we can draw with phasor diagram. Okay, and remaining, we will see OCC, SCC characteristics at the end in calculation of synchronous reactance and all. Okay, basically we are not going to remember anything. You know voltage regulation of transformer? Enough, more than enough. Okay, for example, if I have a generator, okay, generator, this is the output. Okay, so for example, if I connect some load to here, okay, so if I connect some load, then how terminal voltage vary with respect to load current, we need to know. Okay, so externally to the machine, okay, so machine externally, what is about to happen? For example, if you are a layman, which you don't know anything about the machine, you are a layman, you are not an electrical engineer, so for them external characteristics matter, because how VTIA variations are happening, one performance characteristic. Now let us think of like an engineer. Okay, engineer in the sense, in order to maintain terminal voltage constant, how my field current IF, how my field current should be varied, means in order to maintain terminal voltage constant is going to be internal to the machine, which will be maintained by operating engineer. Okay, so that is internal characteristic. Okay, and one more thing is load characteristic will come. As of now, load characteristic, the significance we cannot say. Okay, but it will be used in order to differentiate between XAR and XAL. Okay, so in total excess synchronous reactance, XAL leakage will be there, and because of armature reaction, some X will come. Already we have seen in our previous videos. So in order to have a split between these two, load characteristic will be useful. Okay, so load characteristic means that VTIF characteristic, terminal voltage, field current, okay, for a given IA constant is nothing but full load. Okay, so about this characteristic, you are not going to remember anything. Everything will come automatically in the exam. Okay, so let us see internal external characteristics. We know only voltage regulation. Okay, for example, if I have resistance, reactance, okay, so for example, this is V2, this is V1, or Vx, Vy. Okay, now for example, some current is flowing here, and this is resistance, reactance. Anyway, in our synchronous machine, resistance can be neglected compared to reactance. Now, impedance is there. Okay, for example, if this is lagging in nature, voltage regulation should be positive means that my magnitude of voltage, if you see, compared to Vx, if you fix the Vx fixed, okay, so Vy should be reduced. Okay, or if you maintain Vy constant, Vx should be increased. Okay, so for a given current of lag, my voltage regulation should be positive, means that Vx minus Vy by rated voltage should be positive, means that Vx should be more than Vy. Okay, for example, if Vx is constant, Vy should be less. In order to maintain Vy constant, Vx should be increased. That is voltage regulation. Now, for example, if it is lead, okay, so in leading condition, what will happen in leading condition? In leading condition, voltage regulation is going to be negative. Negative means that compared to Vx, Vy should be more. Because Vx minus Vy by rated voltage is going to be voltage regulation. In leading, it should be negative, means that Vx should be less, Vy should be more. Okay, so if I fix this should be more, or if I fix this should be less. Okay, if you know this, it's more than enough to draw all these characteristics. Okay, so this particular Rx combination can be my generator, resistance, armature resistance, synchronous reactance. Okay, or this can be transmission line resistance, transmission line reactance, or this can be RE2, XE2 of transformer, or this can be R1, X1 of transformer. For example, if I keep a shunt branch here in exact equivalent circuit, if I keep the shunt branch here, R1, X1, R0, X0 transformer. In transformer, if it is operating at lagging, this is infinite source, this voltage should be less. Okay, one means voltage across shunt branch should be less, means that V by F ratio will be less, means that directly B max is directly proportional to V by F, so operating flux density should be less. In that way, in transformer we analyzed. Okay, anyway, conclusion is very simple: resistance, reactance. Okay, under that condition, at lagging condition, if I fix this, this should be less, or if I fix this should be more. Positive voltage regulation. Or at leading conditions means, in order to, for example, if I fix this should be more, or if I fix this should be less. That's it. Okay, now in our alternator, let me keep this Vy as Vt, terminal voltage, let me keep this Vx as Ef, and let me keep this as Ra and Xs, or Ra can be neglected, only Xs. Okay, now let us try to draw a small phasor diagram. What is that? Like, resistance, reactance, Vt, Ef, Ra, Xs, Ia, alternator. Now for example, with respect to Vt, if I try to draw the phasor diagram, Vt at an angle 0. If Ia lag behind, okay, so Ia, Ra in line with Ia, IAXS such that this is going to be EF. So if my alternator is operating at lagging, means that EF should be more. Okay, so in order to maintain Vt compared to Vt, EF should be more. Okay, for example, forget about this Ra because X by R ratio is high. Under that condition, if I try to draw the phasor diagram, this is going to be Vt. For example, if Ia is lagging, okay, now Vt Ia Ra Iaxs. Okay, so 90 degrees lead, so Vt plus Iaxs is going to be F. Vt Ia Ra Iaxs 90 degrees, so with respect to this 90 degrees, Iaxs is going to be Ef. So at lagging conditions, Ef magnitude is more compared to Vt, it should be default. Okay, let us draw one small phasor diagram for leading conditions. In leading conditions, Vt, if Ia is leading, okay, now one thing I have to tell you here, okay, basically many faculties, what they do, they will try to cover up synchronous machines with V and inverted V curves. Should not be, because by V and inverted V curves, if you are deciding or if you are concluding something, that is BTech level. Okay, so here what we have to do, like, we should not go with BTech level because our level is GATE. Okay, so in GATE exam, if you depend upon VN and inverted V curves, like, means we cannot solve the problems, we cannot get the conclusion soon, so we have to depend upon phasor diagrams only. With phasor diagram, just close your eyes, get the phasor diagram, just visualize, enough. Okay, anyway, if it is Vt Ia, okay, Ia Ra will be here, Iaxs will be 90 degrees lead, so 90 degrees to Ia is going to be Iaxs. Ia Ra Iaxs 90 degrees. So Vt plus Iaxs, Vt plus Iaxs is going to be EF. Okay, so this EF is going to be like this. Okay, now length of EF is less compared to Vt. Yes, compared to Vt, EF length will be less. Okay, so EF magnitude will be less, Vt magnitude will be more at leading conditions. For example, in transmission line we have Ferranti effect. Okay, what is Ferranti effect? Like, dielectric will be more, effects will be more compared to inductive effects. When transmission is lightly loaded, something like that we say. Okay, so when dielectric effects are more, receiving and compared to sending end voltage, receiving end voltage magnitude is more. Okay, so here also at leading power factor means that dielectric effects are going to be dominating. Under that condition, Vt will be more, EF will be less at leading. Okay, so if you know these basics, maybe in our previous videos of machines, I clearly said that even though this is less, this is more, how power is going to be transmitted from here to here? Okay, so if this voltage is less, this voltage is more, some people feel like, if this is less, this is more, current should be flowing from here to here. No, why, how current is flowing from here to here? No, that's meant for DC, it is AC. AC in the sense, I told in the previous sessions. Okay, saying like, depending upon the position of current waveform with respect to voltage waveform will decide the direction of power. Okay, so means though it is less, it is more. my position of current waveform in sinusoid will be in such a way that active power will be flowing from here to here only. Okay, forget about all. Let us draw the phasors. Performance characteristics. Again, let me take, forget about resistance. Let us think of inductance. This is XS, this is EF, this is VT, this is IA. Okay, now for example, if IA is increased, okay, maybe let me extend this. For example, this can be resistance and inductance. First, if this is resistance and inductance, how my external characteristics? External characteristics in the sense VT, IA external. Okay, in that case EF will be constant. If EF is constant, VT, IA external. If VT is constant, how to maintain field current such that EF variation should be maintained? If VT is constant, EF will come, that is internal to the machine. If EF is constant, VT, how it is varying, that is external to the machine. So we are trying to draw external characteristics. External characteristics means that how VT is varying with respect to current. Okay, so variation of VT and IA you are considering means that magnitude of EF should be constant. So EF is going to be constant. EF in the sense how to maintain EF constant? Field current is constant, IF. IF is going to be constant. Okay, now under that condition, for example, when IA is 0, when IA is 0, when IA will be 0, this load resistance is infinite, this is infinite. Okay, reactance is infinite, such that total impedance is infinite, IA is going to be 0, it means drop is going to be 0, EF is nothing but VT. So when IA is 0, it will start from EF. This is EF. Okay, now for example, variation of IA you are considering means that one more parameter is there. What is that? Power factor. Okay, so power factor for a given characteristic, power factor will maintain constant. Okay, because variation of power factor, variation of IA, variation of VT, how to draw in two-dimensional graph? Not possible. Okay, so what we are going to do is, okay, means power factor at, for example, 0.8 PF lag. Okay, if you think of 0.8 PF lag, 0.8 PF lag is fixed. Okay, this resistance is infinite, X is infinite, such that IA is 0, EF is nothing but VT. IA is 0, EF is nothing but VT. Now, for example, if resistance is reduced, and in order to maintain 0.8 power factor, reactance is reduced, okay, then what will happen? Lagging current will increase, because reduce, total impedance will be reduced. So total impedance is reduced means that magnitude of IA will increase. Okay, so if magnitude of IA increase at lagging conditions, voltage regulation should be positive, means that if you fix this, it should be reduced. Okay, now for example, if I reduce this resistance still, okay, so resistance is reduced still, reactance is reduced such a way that 0.8 power factor is maintained. Under that condition, total impedance is going to reduce, IA is going to increase. If IA increase, IAX voltage drop will increase, means that VT will be reduced still. EF is maintained constant, VT will be reduced. For example, reduce, increase, reduce, total impedance reduce, IA will increase, so VT should reduce. Okay, so reduce, increase, increase, reduce till what extent you can reduce? Resistance is 0, reactance is 0. Then how much will be the current? Is going to be maximum. Now when this is 0, how much will be the terminal voltage? Is going to be 0. Okay, so when terminal voltage is 0, terminal voltage will become 0. Okay, so my characteristic will keep on reduce like this. Okay, so my terminal voltage, if you keep on increase IA, my terminal voltage reduce, IA will increase. For example, let us think of leading, resistance, capacitance. Okay, so these two also are variables. For example, it is 0.8 lead. Okay, so that is fixed up, because as I told you, only two parameters variation can be seen, shown. Now resistance is infinite, reactance is infinite, total impedance is infinite, IA is going to be 0, voltage drop is going to be 0, EF equal to VT. So when IA equal to 0, characteristics should start from here only. Okay, now resistance is reduced, In order to maintain given power factor, reactance is reduced such that impedance is going to reduce. Magnitude of IA current flowing through this is going to increase. So the moment current increase, okay, EF is going to maintain the same. Leading current, negative voltage regulation. Sending and receiving end voltage should be more compared to sending end. Okay, so when EF is fixed, VT will increase. Okay, so this resistance reduce, reactance reduce, current increase, VT increase. So reduce, IA increase because magnitude of impedance reduce, increase, reduce, increase, reduce till what extent you can reduce? 0. Then again, how much will be the terminal voltage? Same. Okay, 0. Okay, so here when it is 0, when it is here 0, same current should flow or not? Yes, that is nothing but EF by XS. Okay, so if I keep on at leading power factor, my terminal voltage will keep on increasing, and it has to come back to here only. Okay, because when it is 0, current flowing should be same as previous black or not lagging conditions. So it will increase and has to reduce. Of course, this is going to be unstable region. Okay, most of the books, what they do, they will not combine up to here. They will show increment, they will show decrement, up to some extent only. No, it should be extended to steady short circuit current. Okay, so what is this? Is going to be steady short circuit current. Why it is called as steady? Already, like we have seen in power systems, or you can go through the power systems videos of symmetrical fault analysis. Okay, so how much is the steady short circuit current? Is going to be EF by XS because steady short circuit. Okay, so is going to be EF by XS. Okay, for example, if EF is 1 per unit rated voltage, this is per unit, so this is going to be 1 by XS per unit. 1 by XS per unit. Rated voltage 1, XS is going to be XS per unit is going to 1 by XS per unit. In power system fault analysis, Thevenin's equivalent and many things. Okay. Now next thing is, let us see, this is going to be external characteristic. Okay. So this is going to be for lagging condition. This is going to be for red is going to be for leading condition. Did we remember anything? No. Okay. If EF is constant, VT has to reduce at lagging. VT has to increase at leading, that's it. Okay, now let us think of the same internal characteristics. Okay, so if you think of internal characteristics, okay, internal to the machine means that externally, for example, if I maintain VT constant, if load current is increasing, for example, if EF is constant, at lagging conditions VT will reduce. But in lagging conditions, in order to maintain VT constant, EF has to be increased. Means that field current has to be increased. Okay. So for example, internal characteristic, this is going to be IA or load current only. Internal, how EF has to be maintained in order to maintain VT constant. Internally, EF or directly I can say how field current has to be varied. Okay, for example, when terminal voltage is rated voltage at no load, 0 current, under that current 0 drop, this also will become 1 per unit or rated voltage only. So when IA is 0, VT equal to EF. So here it will be VT. Okay, now directly we can draw. Okay, for example, at lagging conditions, if I maintain EF constant, VT will be reduced. In order to maintain VT constant, EF has to be increased. The field current has to be increased. So at lagging conditions, it should be like this. Lagging. At leading conditions, my current has to be reduced, field current has to be reduced. Why? Because at leading conditions, if I maintain this as constant, it will increase. In order to maintain this as VT as constant, EF has to be reduced. So depending upon the load current, it will reduce. Okay, so this is going to be external characteristic at lagging and leading, and this is going to be internal characteristic at lagging and leading. Remaining characteristics we will see in the next video.